Alright, so today I'm going to talk a little bit about light. Light, not necessarily like exactly what it is. I'm not going to go into like waves or particles kind of thing, more of just ways it's used in the sense of like equations, how it relates to wavelength, frequency, um, velocity, and things like that as it enters different mediums, and so on and so forth. So we'll talk about more of those properties and how it's applied, and some more intuitive ways or conceptual ways to think about it, not necessarily the nitty gritty of it. So, first of all, I just want to mention that light, we're going to treat it most of the time here for the sake of our equations, and what we're doing today is a wave. Now, waves follow a pretty strict law here. The velocity of any wave, or the c, you'll see it written as c, sometimes that refers to like a wave's given speed in that medium, is equal to wavelength times frequency. So what that really means is if I have like a wave, let's say like this or something, let's say that's so this is a graph and that's my x-axis there or something like that. Okay, one wavelength would be one full cycle. So it'd be like all the way back to here. So you see how from here to here, that's one wavelength. So it could be other ways too. I could say from here and then go one full wavelength to here, that's still a wavelength. It doesn't really matter where you start and finish, that's just the point. So wavelength is measured in meters. So I could write meters for the units. Let's say I'm doing that. And then frequency is an interesting concept I'll talk about more in a different video, but frequency is basically how many cycles or revolutions or anything else you get per second. So that seems pretty simple, and it is, but with period and things like that, there's tricky questions and things like that that can get people tricked up on. People will say that frequency and wavelength are inverses, for example, and they're not. They're inverses if velocity stays constant, then they're inverses in the sense that if one goes up, the other goes down. However, they're not inverses of each other truly. That's shown by their units. But so frequency is measured in hertz, which is basically 1 over seconds. So I'm going to draw that like that. So obviously the 1 doesn't matter. And so if you notice, it's still equal to velocity, so velocity is meters per second, so that makes sense, right? Anyway, just want to point that out. So, looking at light as a wave, we know, or at least a lot of us might know, or be able to look up the fact that I'm going to round here, but light, or C for light in a vacuum, or for the most part in air, because air has an index of refraction really close to that of a vacuum of 1. It travels at 3 times 10 to the 8th meters per second. Okay, so that's really, really fast. So I'm estimating that, and it's going to make the math easier, but that's obviously really, really fast, and that's the C. So a question that often comes up is, well, does light change speed in different mediums? And the answer is yes, it does. It travels much faster in a vacuum, for example, than it would in a really dense, really thick medium with a high modulus of elasticity. And so in water, for example, I don't know the speed off the top of my head, but it would go slower, water being denser than air. Okay, so it'd be something less than 3 times 10 to the 8th meters per second. So light does actually slow down. And a way we can figure out its speed or whatever is if we had been given wavelength and frequency, we could solve for velocity. But what I really want to talk about is how it slows down. So it slows down and it bends. So let's talk a little bit about like why and how. So let's say I have, let's say this is the air here. Okay, and this is water over here. So water, I don't know how this is happening, but so as light enters, okay, let's say this is a light wave or something, and as it enters the water, it's going to slow down. Okay, it's going to slow down, and we know that because water is denser than air. So knowing that velocity goes down, our question is what happens to wavelength and frequency? So one of those has to stay constant, or else we can't manipulate this equation to give us a variable or a way to look at it. So one thing to remember is frequency, with the exception of Doppler, doesn't change. The frequency of a wave is its identity, essentially. So the only difference between a gamma wave, for example, and visible light, or infrared, or microwaves, or radio waves, is simply its frequency. That's the big difference there. Gamma waves are a type of radiation that's very dangerous, whereas visible light obviously is not dangerous. So the difference is just the frequency of this thing. They travel the same speed. Their frequency is their identity there. So looking at this here, frequency stays the same. I'm going to underline it. Okay, we want to see essentially what's going to happen to wavelength. So in order to keep frequency the same, if velocity goes down, wavelength also has to go down. Okay, so I could rewrite that v over wavelength equals f, right? And that seems kind of weird that if these both would go down. But if you think about it, plug in numbers. If velocity was 10 before, and it's divided by 2 to be 5, and wavelength was 2 before, if you don't drop that by an equal amount, it's gonna change the number, and you want to keep a constant there. It needs to drop by the same amount in order to keep that number the same. So as far as frequency is concerned. So okay, knowing that, what does that mean this is going to look like here? Okay, so as this wave enters the water, wavelength is going to go down. Frequency stays the same. Velocity goes down. So if wavelength goes down, that literally means that the distance from the start of a wave, so I'm going to say here's the start of a wave here, there's the end of that wave, there's one wavelength, right? Let's say this was 1 meter before. Well, once it crosses into the water side, assume that I could actually draw perfect little waves here. From here to here, I'm just going to say, and this is an exaggeration, probably wouldn't change this much, but let's say it's a half a meter. Okay. Now, the question is, doesn't it look like frequency change too? I mean, frequency is how many wavelengths reach a certain point per second. If I were to say this is my arbitrary point, how many waves pass that per second? It looks like that should change too, but remember, velocity goes down. So this is a propagating wave. It's not something just standing there. It's literally moving across the page. It has an end and it has a beginning. And so as it's moving, if it's going slower, but it's shorter, then it's going to cross the same line in the same amount of time. And that's just a property of these waves, and that's important to know. So wavelength's going to go down. And that's what's happening here. Okay. Now, so when water, if that medium was to stop, so let's say I had like air here, and then I entered water, and then it came out on the other side onto air again, it's going to go back to what it was before. So if the wavelength was this before, speeds up in water, it's going to go right back to what it was before. So the velocity of a wave is dependent on the medium. And this is true for light, somewhat for sound, assuming we're keeping temperature and things like that constant or relatively constant. But this obviously isn't true of I don't know, like if I had a rope and I tied it to the wall and I made a propagating wave that way somehow. It's not. I mean, I can change the velocity of the wave all I want, regardless of the fact that I have that rope there. It's not like that if I use a different rope, it's not going to change the speed just by itself. I could do that. However, with electromagnetic waves, which is what light is, it's all about the medium. So wavelength went down as we entered the water, right? And then it's going to go back up as we go back into the air. And it will speed back up. So let's say it's here in the air. It's 3 times 10 to the 8th meters per second is its velocity. Now I'm going to grossly exaggerate this. Let's say here it's 2.9 times 10 to the 8th meters per second in the water. It's going to go right back to 3 times 10 to the 8th meters per second. Now, that seems pretty simple. It's easy to forget. And when we get into Doppler effect and things like that, you'll see why knowing that is important, especially if you are taking a test such as the MCAT, which is full of Doppler effect and light properties. So that's all I'll put for this video. I'm going to keep it around 10 minutes. Try not to ramble too much. And in another video, we'll talk more about how light bends with refraction, for example. We'll talk about sound waves and ways to calculate different, just general equations of velocity, wavelength, and frequency. So thank you for watching.